Okay, so for relative velocity, in this question, what we've got is it's the kind of typical police officer speed trap. The police officer has their radar gun and they're aiming it towards cars to try to figure out how fast these cars are going. The trick here is the police officer can see car A but can't see car B because it's kind of in behind car A. And we have to just use a little bit of imagination here. Let's imagine the police officer can see that car A is going 50 kilometers per hour, but can't see how fast B is going. So just imagine if the police officer could call car A, let's say it's their friend in car A, they call them and they say, how much faster is car B going than you? And again, somehow car A, maybe they got their own speed gun or something, they say this car is going 20 kilometers per hour faster than I am in car A. This becomes an easy question then. The police officer is gonna be able to tell that car B is just going the sum of these two. 50 plus 20, it's going 70 kilometers per hour. This is an easy question because it's a simple setup, but these questions get much harder. And so what we wanna do is we wanna use this setup to try to find a reliable way to know how to add these things, add these vectors together so that when we get to harder questions, we can have a reliable way to do this. So people have come up with these subscripts. So what the subscript here means is how fast is car A going to the police officer? So the velocity of A relative to the police. This subscript here shows how fast B is going, but relative to A. So velocity of B relative to A, in this case, is 20 kilometers per hour faster than A. What we want to know is how fast is B going relative to the police officer. Okay, so here's our subscript equation. The subscript equation, we're going to say VBP, so how fast is B going relative to P. That is the sum of B to A plus A to P. And what we can see in the subscript equation here is that the first one here matches the first one here, the last one here matches the last one here, and A are the same. You can kind of think of it like those two cancel out. So if I add these two vectors, remember these things are all vectors when we do this. When I add these two vectors, the A's cancel out and what I'm left with is BP, which is what I'm looking for. Okay, so that's how the subscript equation works. Sometimes I like the subscript equation, sometimes it's helpful, especially if you're using kind of component method techniques. If you're not using component method techniques, then it's not as helpful. Okay, so we're gonna try to do this with a couple of these questions. Let's see, here we go. I've got one where we've got this person, so Nawal is in a subway. So Nawal is walking 3 meters per second east. So let's say this is Nawal right here. This is the subway car. You can imagine there's some wheels down here and the subway is moving this way. If Nawal walks at 3 meters per second east, so I'm gonna say it's the velocity of Nawal relative to the subway car, if we can kind of give things letters. The subway car though is going 25 meters per second. So this is 25 meters per second. This one is 3 meters per second. The subway car is going 25 meters per second. If we just say that the subway car is going that fast, what we really mean is relative to ground. So if down here is the ground, we've got Nawal, subway, and ground, this becomes the velocity of the subway car relative to the ground. Okay, so we've got VSG, we've got VNS. What we want to know is how fast does Nawal, how fast does Nawal appear to be moving relative to an observer on the ground? If you can imagine an observer out here, they are stationary relative to the ground. So instead of observer, I'm just going to say ground because that's what I've called it. You could have called it observer, in which case this would just be an O out here. So what I'm looking for then is how fast, here, let's go here. How fast, what's the velocity of Nawal relative to ground? That is going to be velocity of Nawal, so I want N first, so Nawal relative to subway car plus subway car relative to ground. So the N's line up, the G's line up, my S's, again, you can kind of think of those things as canceling out. I do need to consider these things as vectors though, so I'm going to stick with east being my positive direction. So again, this is probably one you could do in your head, but they will get harder, I promise. East is positive, so this this VNS here is 3. VSG is 25. If east is positive, this is west, it's going to go in as negative 25. velocity of Nawal to ground is -22. That's meters per second in my positive direction. Again, first answer is always in the positive direction, but it's negative, so I'm going to rearrange or make it positive, 22 meters per second, and write it as west. Okay, so again, this is a really easy question. It's one you could do in your head, but they will get harder, and this just indicates how we can do these questions. Okay, so if we get to a little bit harder one now, what we've got is we got Akshaya, in this case, is walking at 3 meters per second north. Okay, so here's my 3 meters per second north. I already included the subscripts here. This is Akshaya compared with the subway car. So here's Akshaya, here's the subway. Again, this is a top view, so I won't draw the surface of the ground, but somewhere out here is the ground. We know that she walks at 3 meters per second north, but the subway itself, subway to ground, is going at 10 meters per second east. She starts from the south wall, okay, so she's starting here and she's going across this way. And then the subway car is 4.2 meters across. Okay, so now we got some questions to answer. What's her velocity relative to ground? Let's see, I'll see if I can squeeze it down here a little bit. What we want to know is what is Akshaya's velocity relative to ground? And again, if you think of your subscript equation, I'm going to start with A. So there's my one that starts with A. I need S to come first and G to come last. So this is working out nicely. Now keep in mind, these are vectors. Okay, so you could say, I'm going to do this. VAG is 3 meters per second. Just remember, this one is east. Plus, I'm adding to that 10 meters per second. Sorry, this one's north. This one here is 10 meters per second, and this one is east. I do want to add these, but I can't just say it's 3 plus 10 is 13 because these vectors are not in a straight line. They're not linear. That means I'm going to have to redraw this thing. Okay, so the way that we add vectors like that is VAS is going this way. Again, that's 3 meters per second. We've got VSG going this way, 10 meters per second. The way that we add them then is to draw them tip to tail. We're going to use some Pythagoras. We'll use some trig as well to find out this angle. Okay, so this is Akshaya to ground. What we're going to say then is VAG is, just using Pythagoras, the square root of 3 squared plus 10 squared VAG. What does that end up being? .44 meters per second. This is only 2 sig digs, but just so we can distinguish from the original 10 meters per second here, I'm going to leave it as 3 sig digs just so we can see that the difference that's there. So 10.4 meters per second. We do need a direction over here, so I need to know this angle. We can say tan theta, opposite over adjacent, 10 over 3, 73 degrees. So this would be north, 73 degrees east. And there's our answer for that part. Part B then asks, how long does it take her to cross the car? And this is one of these simple, we're just using velocities, displacement over time. I'm going to rearrange. Time is displacement over velocity. Now the question is, what numbers am I using? So for example, for D, I want to use this 4.2 meters. That's the only distance that I've got. But then the question is, which of these velocities do I use? 10.4 or 10 or 3? Which one am I using? And if you think about it, this one here is going straight north. I need to use a corresponding velocity. Okay, if we were talking about how long does it take me to travel, 100 meters east, then I'm going to use this velocity. In this case though, to get across the car, really what I want to know is how long does it take her to go 4.2 meters north? I need to use a velocity that is also north. Okay, so what we're using here, if I was to put in some subscripts, I guess I would say it's the displacement of Akshaya to subway. I'm going to use velocity of Akshaya to subway. Then it's just easy. The displacement is 4.2 meters. The velocity is 3. Let's see, that is 1.4 seconds. And we'll see if we can squeeze C down here. Hopefully I've got just enough room. What is her displacement relative to the ground in this time? Again, I'm using the same equation. If I rearrange it, D is V times T. My only question is which corresponding displacement and velocity am I going to use? And like we did here, you can think of it as putting these subscripts in. I'm looking for Akshaya to ground. So the displacement Akshaya to ground, I need to use velocity Akshaya to ground. In that case, the displacement Akshaya to ground is, let's see, her velocity relative to ground is this one. I'll use 10.44 times the time. And in total, she traveled for 1.4 seconds. Just remember, like in projectile motion, if you find think of this as the y direction. If you find the time in the y direction, you can use it in the x direction. That's the same principle going on here. The time, whether she's going this way or going this way because the subway car is moving that way, all the times are the same. I'm going to multiply this and I get 14.6 meters. Now, what direction would this be? You might ask. Glad you asked. The displacement's direction is in the same direction as that velocity, which would be this one right here. So north 73 degrees east. This is actually displacement. So just remember, this displacement is kind of going, I kind of don't have a lot of room here, but she aims this way. The subway car, though, kind of pushes her this way. The result is she ends up going this way. It's the same triangle. She ends up going, her displacement is 14.6 meters there at an angle of north 73 degrees east. Okay, so you can imagine the same triangle, they're similar triangles, just using distance or displacement measurements over here. And hopefully you can see that whole thing.